Hello chemists, this is Miss Placino and you are watching Screencast 10.3 on determining concentration. In today's lesson we're going to talk about how to express the concentration of a solution. It turns out there are a variety of different ways to express concentration, and the one that you pick is really going to be dependent upon the situation and the nature of the solution itself. For chemistry we're going to focus in on just a couple of them, so don't panic if you're looking at your workbook and you think that's a lot to remember. We'll get down to the most essential ones once we get going. So when we're talking about concentration, we're really looking at the measure of the quantity of solute dissolved in a given amount of solvent, or for the solution in general. We want to be specific with concentration. Just using the terms diluted versus concentrated can be really vague and overall not too helpful. We want numbers there so that we can really compare concentrations. If you look at I guess they kind of look like glasses of Kool-Aid in the slide, it's easy to tell because the solution is colored, which one has more solute molecules in it, which one has the least solute molecules in it. Hopefully we would see that this diluted one is barely pink at all, has very few solute molecules, while as we move all the way to the right, things are gradually becoming more and more concentrated. But you might want to know how much solute is in there, and that's what we're going to focus on today. How do we express concentration? You're going to want a calculator, you might need a reference table, and really you can follow along with what I'm doing in your workbook. So that is pretty much it for PowerPoint today. We are going to put the pencil on the paper and get through a lot of these problems. Alright, so as you can see there are 6 different ways we're going to learn how to express concentration. And again, don't worry, I know that seems like a lot. We'll tell you which ones really to focus on. So we're going to start with percent concentration by mass. And this is really useful if you're trying to express concentration to someone who's not really chemistry savvy. A lot of times you'll see this on consumer products. They might tell you the percentage of sugar and stuff in different products. So when we're trying to find percent mass, looking for mass of solute divided by the mass of the solution. And because this is a percentage, we of course want to multiply it by 100. Now in order to find the mass of the solution, you could just take the mass of the solute plus the mass of the solvent. Masses are additive. For example, if you take your own mass by standing on a scale and then you take a 10-pound weight and you hold it and then you step on the scale again, you can just add the masses together. So your weight plus the 10 pounds, whether you measure them separately or combined, is going to be the same number. So let's take a look at a practice problem. A student dissolves 25 grams of glucose in 475 grams of water. What is the percent concentration by mass of glucose in the solution? Since there's not a lot of space, I'm not going to rewrite my formula, but I'm going to take the mass of the solute, in this case the glucose, 25.0 grams. I'm going to divide by the mass of the solution, and as we just discussed, you find that by adding the mass of the solute plus the mass of the solvent. That's 25 grams plus 475 grams times 100. So you might have simplified that right off the bat and went to 25 divided by 500. I'll pull up my calculator. 25 divided by 500 times 100 because it's a percent. And we end up with something that's 5% by mass. If I'm going to pay attention to significant figures here, why not? 5% glucose by mass. So hopefully that one's pretty easy to follow. If I'm looking for the percent concentration by mass, I need to know something about the mass of my solute, my solvent, so that I can ultimately find the mass of the solution. Let's take a look at the next one, percent concentration by volume. This is another one that's used a lot in commercial products. For example, if you go and you buy rubbing alcohol for a first aid kit, you can buy them at different percentages. They always just mix it with water. So if we're going to try to find the percent concentration by volume, we're going to take, probably could guess this, the volume of the solute, divide by the volume of solution, and then we'll multiply by 100. One thing to be careful with here, this isn't something I'm going to try to trip you up with when you go to take your test, but just something to be aware of. The volume of the solution does not equal the volume of the solute plus the volume of the solvent. Unlike masses, volumes are not additive. This may seem kind of strange, but if you take, let's say, 100 milliliters of water and 100 milliliters of rubbing alcohol and you mix them together, common sense would tell you that you should have 200 milliliters of solution. Surprisingly, that is not what happens. Due to the interaction, like the intermolecular forces between rubbing alcohol molecules and water molecules, both are polar, they're going to kind of fit together a little bit more tightly than you might anticipate. And instead of seeing 200 milliliters of solution, you might see closer to, I don't know, maybe 195 or so. So we cannot add volumes together. So I'm going to have to give you that information. If we take a look at a practice problem, it says a solution is prepared by dissolving 90 milliliters of hydrogen peroxide in enough water to make 3,000 milliliters of solution. So here we don't add them. You're told the volume of the solution. And again, since volume in general is not additive, I really have to tell you the total volume of the solution. So let's take a look. Whoa. Zoomed in a whole lot more than we needed to. I've got 90 milliliters. I'm going to divide by my total volume of solution, in this case 3,000 milliliters, because it's a percentage. Ooh, got a little carried away there. Multiply by 100. So we can do the same thing. Use your calculator. We've got 90 divided by 3,000 times 100. And this one we technically only have one significant figure, so I end up with 3% concentration by volume. One thing to keep in mind as you're trying to calculate things like percent concentration by mass and percent concentration by volume is to be careful with your units. Units are extremely important. They're not just there for decorative purposes. They have real meaning. When you go to find percent mass and percent volume, you want to make sure that you are using the same units in both the numerator and the denominator. So for example, let's go ahead and get a different color pen. Everything's in grams. We're talking about percent concentration by mass. Everything's in milliliters when we're talking about percent concentration by volume. You can imagine the number or your answer is going to change pretty dramatically if instead of saying this was 3,000 milliliters, I just wrote it instead as 3 liters. If you just blindly start plugging and chugging and you don't think about the units, you're going to come up with answers that are off by, in that case, a factor of 1,000. So really be careful with your units. I highly recommend taking that extra couple of seconds for each number you write and include the units with it, hopefully to prevent you from making kind of careless, silly mistakes. All right, put a star next to the parts per million one. This one does show up on your reference table. In order to calculate parts per million, we're going to take the mass of the solute, divide by the mass of solution. You'll be thinking, wait a second, we already talked about this. The difference is, then we're going to multiply it by 1,000,000 times 10 to the 6. Parts per million are used frequently when you're talking about concentrations that are very, very low. A lot of times environmental pollutants, things like lead, for example, are going to hopefully be expressed in parts per million. So they'll talk about pollution in terms of 20 parts per million of a certain molecule was found. This is just a much more convenient way than saying 0.00015% by mass of a certain molecule or ion or element was found. So a lot of times you'll see this in reference to pollution. Here's another another type of problem where you want to make sure units match. A lot of times the mass of the solute is so small it's going to be expressed in a smaller unit than the mass of the solution or the mass of the solute. The solvent. So be careful about that. Again, it's really easy to make careless mistakes and get yourself in a lot of trouble. So let's take a look at this question. A certain gas has a concentration of 2 milligrams per 100 grams of water. What is the concentration of the gas in parts per million? All right, if I'm paying attention to units, I see milligrams and I see grams. Obviously, they are not the same unit, so I need to convert. It doesn't really matter if I convert milligrams into grams, or if I take grams and I convert it to milligrams. Whatever works out best for you. So there are 1,000 milligrams in a gram. so I'll do without the work. So 2 milligrams times 1 gram over 1,000 milligrams. We get 0.002 grams of this gas. Now I can plug in. I know the mass, oh, what happened there? I know the mass of my solute, 0.002 grams. I know the mass of the solution. Some people will go ahead and add in that 0.002 grams. Technically, from a significant figure perspective, you really shouldn't. But the bottom line is it's going to make a pretty minimal impact on your data in your calculation, I should say. So I've got 0.002 grams divided by 1,000 grams. Divided by 100 grams times 10 to the 6th. Be really careful with your decimal point and how you're entering the times 10 to the 6th term into your calculator. It's really easy to make careless mistakes and end up off by an order of magnitude or two. When you grind through the calculation, you should end up with 20 parts per million. That's it. Again, that one's on your reference table, and that will show up on like New York State Regents exams from time to time. All right, mole fraction we use when we're talking about things in terms of moles, and a lot of times this is most useful when we're talking about gas laws. We're not going to use this too frequently, but I just want you to be aware that it exists in case you take AP chemistry. So to find the mole fraction of A, I'm going to take moles of A, and I'm divided by mole of A plus mole of B plus mole of C plus so on and so forth for however many components are part of that mixture. As the name suggests, make sure that you are working in moles. It really does not work out so well unless you are in the mole. So this one is relatively straightforward. A solution is prepared by combining 3 moles of Cl2 gas with 9 moles of CH4 gas. What is the mole fraction of chlorine in this solution? So I take my moles of chlorine, in this case 3 moles. Let's be careful with sig figs, 3.0 moles. I'm going to divide by 3.0 mole plus 9.0 mole. And then I'm going to end up with, and it's okay to leave this in fraction form, not a lot of times we do that in chemistry, but I can get that down to 3 over 12, which is 1/4, which is equal to 0.25. Pick one, it really doesn't matter how you express it. Since we've got moles divided by moles, they're going to cancel out. So this is actually unitless, which is good news for those of you who are always forgetting units. Okay, we saved some of our best ones for last. Put a lot of stars around molarity. This is a chemist's favorite unit to express concentration of a solution. Molarity is abbreviated with capital M. And this is actually moles of solute divided by liters of solution. Something to be careful with here is just really watch your units. You have to be in moles of solute per liter of solution. Now you've got this formula on the reference table as well, and you can solve by plugging into a formula, or you can solve through dimensional analysis. I'm going to show you both ways. It really depends on the situation as far as which one's going to be easiest to work with. So if we take a look at the question, you have dissolved 0.83 moles of calcium chloride in enough water to make 350 milliliters of solution. What is the molarity of the solution? All right, so this one's probably a time where it's just easier to go ahead and use the formula. Actually, it doesn't really matter. It's always moles of solute, in this case 0.83 moles, divided by liters of solution. Be careful with your units. I've given you a volume of solution in milliliters. You need to convert. So there are 1,000 milliliters in a liter. That means I can move my decimal point over 3 places to the left. And I'm left with really just that. And I just kind of have to plug in and solve. So if I take 0.83 and I divide it by 0.3500, to the correct number of sig figs, I would get about 2.4. We use capital M as the abbreviation. We call it molar. I'd say this is a 2.4 molar solution. All right. And last but not least, we have something called molality, and it's lowercase m. I know that molarity and molality, they sound pretty similar. Their abbreviation, capital M versus lowercase m, is very similar. Even their formulas, mole of solute divided by mass of solvent. It's going to be in kilograms. So be careful. I know, again, they're very, very similar. Make sure that you are reading carefully and that you keep these two separate in your head. Molarity is on the reference table. Molality is not. Molality is really only used, at least for our purposes, in one specific instance, and it's going to be used for colligative properties. In lesson 10.5, we're going to be discussing colligative properties, and when we go to make any calculations regarding them, such as freezing point depression or boiling point elevation, we need to use molality. The application of this formula is pretty straightforward in this case. It says a solution is made by dissolving 1.55 moles of sucrose in 2 kilograms of water. What is the molality of this solution? So first off, read carefully. Molality versus molarity. Second, you've been given a mass of solvent. That's another kind of dead giveaway that you're going to be asked for molality. So we're going to take the moles of solute. In this case, 1.55 moles of sucrose. We're going to divide by the mass of the solvent, 2.00 kilograms. And when we go ahead and we perform that calculation, we end up with 0.775 molal. Please be careful on written work when you're expressing concentration and molarity and molality that you really differentiate between the capital M and the lowercase m. Notice that mine are really different looking. If you kind of just generically slap an M next to it and you're not careful about the size, I'm not going to know whether you mean molarity or molality. Please don't leave it up to me to figure it out. Before we call it a day, I want to talk about a more realistic looking molarity problem. So go ahead and take a look at question number 2. Question number 2 says, what is the molarity of a 450 milliliter solution that contains 200 grams of iron 2 chloride? This is a little bit more in line with what you can expect to be doing with molarity. I'm not just going to simply give you the number of moles and just have you plug in mindlessly to that formula. This is a little bit more practical application. The first thing you need to do is figure out what the formula is for iron 2 chloride. And I think a lot of reasons students struggle with the solutions chemistry unit isn't due to the new concepts that are introduced. It's forcing you to rely on or remember previous concepts. For example, taking a name and turning it into a formula, doing mole conversions, remembering polarity, for example. So iron 2 chloride, iron 2, so that's going to be Fe with a charge of 2+, reacting with a chloride ion. Chloride is a group 17 ion, so it's going to have a charge of 1-. So when they come together, we're going to get FeCl2. So I know the formula of iron 2 chloride, I have the mass of that in grams, and I know the volume of my solution. For molarity, I need moles per liter. So hopefully it's pretty easy to see where the liters are going to come from. I can quickly take my solution volume, 450 milliliters, and convert that into liters. It's going to be a little bit more work to figure out the moles of solutes. What you need to do is find or calculate the molar mass of iron 2 chloride. So I'm going to go ahead and do that now. I know that iron has a mass of about 56 grams per mole. I know that chlorine is about 35.5 grams per mole, so times 2 gives me 71. So I get about 127 grams per mole. Now you might have remembered me mentioning that there are 2 different ways you can attack molarity problems, by trying to sub into that formula or the more practical way, dimensional analysis. I'm going to show you the formula method first. So using the formula method, I've got 200 grams of iron 2 chloride. I know that I need to get to moles over liters. So every time I have 1 mole of iron 2 chloride, it must weigh 127 grams. Grams will cancel out. So just a straightforward mole conversion. And we end up with, take it out to a couple of sig figs, 1.57 moles. I know that molarity is equal to moles over liters. I know the number of moles. I found the volume of my solution. Should be a little bit more careful about how I do that. 0.450 liter. And I come up with a molarity of about 3.50 molar. That's the formula method. I still have a whole lot of work to do. I have to get out of grams of iron 2 chloride and into moles, so I needed to figure out the formula of iron 2 chloride, calculate the molar mass, and then make the conversion. I know not all of you like using formulas, in part because you have to actually show me this extra step. If you don't want to show the formula and you don't want to use it, that's totally fine. To be honest, I don't use it. I use dimensional analysis. So again, I have 200 grams. I know that I have a molar mass of 127 grams per mole. And I know that molarity is expressed in terms of moles per liter. Grams cancel. I'm left with moles. So you can save yourself a little bit of writing by using dimensional analysis instead. Hopefully it's pretty easy to see that you're going to come up with the same exact answer. 200 divided by 127 divided by 0.45, and of course I end up again with 3.50 molar. Now that M is a little bit sloppy. There we go. So pick the method that works for you. If you feel more comfortable with the formula, make sure you're showing your formula. You know I'm a big stickler for that. And if you would rather use dimensional analysis, that's totally fine too. Again, pick what works best for you. As always, there are a ton of practice problems for you to play around with. I really recommend trying them out. Calculating molarity is going to be pretty essential in this unit and as we move forward into other units. All right, sorry this was a little bit on the long side, guys. Thank you for tuning in, and I hope you found this helpful.